let's talk a little bit more about what parsing entails. So parsing is the process of taking text input, which represents a computer program or some other formal language expressions, and turns those into some sort of object that represents the expressions while validating their syntax. A parser takes text and returns expressions, and it does it through an intermediate called tokens. So lexical analysis is the process of breaking up text into tokens, which are words or individual symbols. And then we do a syntactic analysis to figure out how those symbols nest into hierarchical expressions. So let's look at some examples here. Let's say I typed in the following 3 lines. Open paren plus 1, and then on the next line, minus 23, and on the next line, we have another sub-expression, times 4, 5.6, and then closing parenthesis there, closes this one, and then we finally have the closing parenthesis for the original opening parenthesis 2 lines before. The process of lexical analysis breaks up each line into the right pieces for input into syntactic analysis. These are the pieces that represent whole numbers, or special symbols like parentheses, or symbols in the language, such as plus. So this line becomes these 3 tokens. White space is ignored. This line becomes 1, 2, 3, 4 tokens. So notice that 23 is all one token because it's all one number. So lexical analysis is doing some work. It's figuring out that 2 and 3 next to each other really means the number 23. Now notice that this has ignored the white space in the front. So part of lexical analysis is figuring out what to discard, and it's put together 23. Okay, let's look at the third line. How many different tokens are there in this line? 1, 2, 3, 4, 5, 6. So each closed parenthesis is its separate token because it's a special symbol that has some meaning in the language, and these need to be balanced. That's going to be the job of the syntactic analyzer to figure out. But the lexical analyzers figure out that 5.6 is really all one token. So this is an iterative process. It goes through each line and breaks it up into tokens. It checks for malformed tokens. It determines the type of each token. So it's figured out that this is a symbol, whereas this is a number. And it processes one line at a time. That's lexical analysis. Syntactic analysis processes all of these lines together to give us an expression in the language that we're trying to parse. So the result will be a pair where the first element is plus, and the rest of the pair is everything else in these 3 lines, which can be printed as plus 1 minus 2, 3 times 4, 5.6. Now, we've done more than just delete all the white spaces and put it on one line. We've actually figured out the structure of this thing, balanced all the parentheses, meaning we verified that they were balanced in the input, and created this nested pair structure, which happens to be printed out in a nice clean way in scheme expressions. So this is a tree recursive process. It balances parentheses. It returns a tree structure represented by pairs, and it processes multiple lines. So recursive syntactic analysis is a standard problem in computer science. It shows up all the time. And we're going to build a particular kind of parser for the scheme expressions that we want to parse. It's called a predictive recursive descent parser. And that's special because it only needs to inspect k tokens to decide how to proceed, meaning what sort of structure it's going to build. And it does this for some fixed k, meaning it never needs to look that far ahead in order to understand what's going on in the program right now. So let's try a recursive descent parser on the English language. Can English be parsed via predictive recursive descent? Well, how about this sentence? The horse raced past the barn, fell. What? Well, actually, this is a well-formed sentence in English. It's just a little bit unusual. Here, let me tell you how to read this sentence. Think about raced as a synonym for ridden. Like I raced my horse means I rode my horse. And that was has been omitted from this sentence, which you can do. The boat that I was sailing is the same as saying the boat I was sailing. So that can be dropped. And so now think of this sentence as the horse that was ridden past the barn fell. Poor horse. So this whole thing is a sentence subject. It was in the original version of the sentence. It's just a little bit easier to read now that I've changed the sentence slightly to have exactly the same meaning as it had before. Now the reason this is a hard sentence to read is that when you read the horse raced past the barn, you've assumed a structural analysis that has this is the verb, this is the subject. And this is a modifier of the verb telling you where the horse raced. But it was not the horse that was racing at all. Somebody was racing the horse. But we had to look all the way down here to the word fell in order to resolve that structural ambiguity. So English language is not something that you can parse with a recursive descent parser. But fortunately, scheme expressions are. So syntactic analysis in scheme expressions and in programming languages in general can use recursive descent parsers. And what it does is it identifies the hierarchical structure of an expression, which may have some nestings. Each call to scheme read, which we saw briefly before, consumes the input tokens for exactly one expression. The base case is that you find just a symbol, or a number. But there's a recursive call whenever you see an open parenthesis, then you know that's a combination with expressions within it, and each one must be scheme read itself. So when I have an expression that's nested like this, my first call to scheme read will notice that I've started a combination and therefore will have a sequence of sub-expressions until I close that parenthesis. The first one is a base case, just plus. The next one's a base case, just 1. But the next call to scheme read is going to do a bunch of work. It's going to read the whole next expression, which is this thing in parentheses. The next call will read the next sub-expression. And then finally, it will have found the end of the expression that it started in the beginning. That's how scheme read works. Okay, so let's read the code really quickly together. Scheme read, some source tokens. If we ran out of tokens, then that's called an end of file error. Otherwise, get the first token, source.pop. If it's nil, that's a base case. If val is not in delimiters, meaning it's not one of an open paren, a closed paren, a quote, or a dot, then we would just return that value. So that's when we get numbers and symbols as a base case. Otherwise, if we've just opened up a combination with an open parenthesis, then we have more work to do. What do? Well, we return the remainder of the list in source, starting before an element or close parenthesis. Okay, so if we run out of text here, that's a syntax error. But if we find a close parenthesis to match the open parenthesis, then that's a base case and we're done. Otherwise, we find the first element, the rest, and return a pair containing the first and the rest. And first is a recursive call to scheme read, which means that if I read a nested expression that looks like this, what happens is I find this, recursively call read tail, which it calls scheme read to read this expression, which is used as the first element in this pair. Then the second element is a pair 3 nil, giving us the rest of the list.